Hi, this is Mr. Pinter, and welcome to Chapter 4 on the continuous time Fourier transform. In Part 1 of this video lecture, we will be looking at the Fourier transform for aperiodic signals. So Chapter 4 is broken up into 4 parts. This is Part 1, where we will be looking at the Fourier transform for aperiodic signals. In Part 2, we'll basically be doing the same thing for periodic signals. Part 3 will deal mostly with the frequency response and convolution property, a couple of things that we've already been introduced to in the previous chapter. And then the last part of this lecture will look at system analysis using Fourier transform methods. So let's start off by asking the question, why do we want to do all of this Fourier transform stuff? Why do we want to work in the frequency domain instead of just working in the time domain? So there are lots of reasons for this. The first one is by working in the frequency domain, we can avoid complicated convolutions and replace them with simple multiplications. And so this is a refreshing development here where we don't have to do all those convolutions that we learn about in Chapter 2. The second part here, or reason, is that we can find the frequency response of a system. And that's we kind of have already seen this in Chapter 3. The frequency response of a system tells us how the system behaves at different input frequencies. And it's an extremely important analytical tool to analyze a system, to work in this frequency domain and see how the system responds to different frequencies. Oftentimes, the most important reason for working in the frequency domain with Fourier transform is that we simply want to find the output of the system. In other words, if we have some signal x of t going into our system, we want to know, what is the system going to do? How is it going to respond? What is the output of the system going to be? And we can show that we can do this basically using Fourier transform methods. We'll learn how to solve linear differential equations, and we learned earlier in the course that differential equations describe many continuous time systems. So oftentimes the problem is simply we need to solve this differential equation that describes a system, and we will be able to do this using a very clever and elegant solution using Fourier transform methods. We can often solve linear differential equations simply by inspection, which is really a neat trick, and we'll learn how to do this later, not in this part of the video, but in one of the later parts of this chapter we'll do that. Later in the course, where we do more applications of all this theory, for example, we'll talk about filter theory and applications, something that you've already been introduced to in Chapter 3. Chapter 7 is on sampling, and sampling theory is based on Fourier transform methods, and then also communication systems, which is the topic of Chapter 8, also relies heavily on Fourier transform methods. So there's plenty of reasons for doing this somewhat abstract analysis in the frequency domain, and as we do it more often in this course, it'll just become more comfortable for you, and pretty soon you'll be very used to working in the frequency domain versus the time domain. So let's get started with our introduction of the Fourier transform. I'm not going to show a formal derivation of the Fourier transform. Your textbook shows more details if you're curious about how it works, but we can kind of conceptually see what it's about. If we start with a periodic signal, like this periodic square wave here, and we look at its Fourier series, all the Fourier series components here, those are these vertical lines shown here. And we see that this is a discrete spectrum here that has a value at each value of harmonic frequency. Now, if we take this periodic square wave up here and separate the pulses here by more time in between them, notice what happens down here in the spectrum. The frequency components become closer together. They start to crowd together. And if we keep doing this, notice here we're really separating these pulses by a large amount of time, with relative to the small width of the pulse here. Then look at the frequency components down here. They're really bunching together. In fact, if we keep doing this, and if we take the separation here all the way out to the limit of infinity, these frequency components become basically so crowded together that they're basically touching in the limit, and they form a continuous or a continuum of frequency components, which is represented by the solid line, kind of the envelope of these frequency components. So this is sort of the idea of what a Fourier transform is for an aperiodic signal. All right, so here is the again, without showing the formal derivation, it's more important that we just have the results here so that we can use them and apply them. This is the so-called Fourier transform pair for aperiodic signals. So there are two equations here. The first one is an equation for x of t. So this is called the synthesis equation, but it's also called the inverse Fourier transform, because what this equation does is it takes the Fourier transform, which is x of j omega, and it puts it inside this integral to compute the signal in the time domain here. So this was how you would go from Fourier transform back to x of t. So we're going from uppercase t Fourier transform to lowercase t, which is the time signal. Now the other member of this pair, which is really what this chapter is about, this is the definition of the Fourier transform, or likewise we can call it the spectrum of any signal x of t. So in other words, this equation here is sort of like a recipe of how to calculate the Fourier transform for any signal x of t. All we have to do is take x of t, whatever its mathematical form is, and put it inside of this integral and compute this integral. So notice it's an integral in time over all time from negative infinity to positive infinity, and we take the signal x of t and we multiply it by this complex exponential e to the minus j omega t, and this will give us a function not of time but a function of frequency. So notice that the Fourier transform here, x of j omega, is a function of frequency omega, not a function of time. All right, so this is the this is the frequency domain version of our signal. And just to be clear on the convention here, signals in time always use a lowercase letter like small x, and the Fourier transform, which is a signal in frequency, uses the uppercase version of the letter. So that's another way to kind of quickly see if we're talking about a signal in the time domain or the frequency domain. So the so what do these equations mean? They're kind of bizarre looking, right? They're integrals with complex exponentials and so forth. So what do they physically mean? Well, the synthesis equation, if you think about this, remember what an integral is. An integral is a sum of a bunch of tiny little pieces. So each one of these pieces is a frequency component that has a frequency of omega, and the weight or the coefficient of that frequency component is given by the Fourier transform. So we can think of taking a function x of t in time and think of it as sort of breaking it up into an infinite sum of frequency components that each one is weighted by the Fourier transform. On the other hand, the Fourier transform x of j omega tells us basically what the frequency components are, how they look in terms of frequency. So in other words, the Fourier transform gives us the spectrum of the signal. So in this example here, notice this is the Fourier transform, big X of j omega, and this curve here tells us where the frequency components of x of t r. So in the time domain, x of t might look something like this. In the frequency domain, it's going to look something very different, because here we're looking at the spectrum of that signal. What is the frequency makeup of the signal? You can see that in this is just a hypothetical example, but basically it's showing that the signal has, lots of frequency components at low frequencies near 0, but at high frequencies, notice this signal basically has nothing. So let's get started with an actual example. This is a very important signal that we're going to see very often in the course. This is an exponential signal. And again, the reason this signal is so important is that exponential functions solve linear differential equations. And remember that continuous time LTI systems are described by differential equations. Therefore, their solutions usually involve some sort of exponential functions. So this is a real exponential function. In other words, e to the minus at, we're going to assume that a is a real and positive number. A can be something like 1 or 2 or 3.7, something like that. And also this function is what we call right-sided. It has a step function attached to it. That means that this function, remember the step function, is everything to the right of 0. So this function starts at 0 and it goes to the right in time. There's nothing back here. The value of the function would be 0. So this is what the function looks like. It's obviously an exponentially decaying function with time. So let's go ahead and see if we can figure out what the Fourier transform of this signal would be. So here's our Fourier transform integral. All we have to do is for x of t right here, just plug this in to the integral. So I've done that here. You can see the e to the minus at is plugged in there. Now what does a step function do? Well, the step function says that this signal, x of t, only exists from 0 to positive values of t. So notice the limits of integration here. We're not going to integrate from negative infinity to infinity. We have to change the limits of integration to 0 to infinity, because this function has no value for negative values of time. So there's two things we did here. We plugged in e to the minus at, and we used the step function to change these limits of integration. Now this integral here, at first glance it looks kind of nasty, but it's really not. Let's go ahead and factor out, notice both exponents have a t. So we can combine those exponents using the simple law of exponents for exponential functions, and we add these two exponents together. And so I'm going to put a minus sign out in front, and in parentheses I have a plus j omega, and then there's the t. Now this is actually now a very standard integral. You know how to integrate exponential functions from calculus class. So whatever's in front of the t here, we put that down here on the bottom. So I'm going to put the minus sign up here. It doesn't matter. We have minus 1 over a plus j omega, and then we have the exponential function here, and we have to evaluate this thing from 0 to infinity. So the next question is, well, how do we do this? Here's this exponential function here. How do we evaluate this? Because it's got a real part and it's got an imaginary part. Well, the easiest way to do this is to break this exponential function back up. So notice, up here we combined the exponents to get this. Down here we're going to go in the reverse direction. We're going to start with this, and we're going to split it back apart, kind of like it was up here. And now we'll be able to evaluate this much easier. So the real part here, e to the minus at, notice when we plug in infinity for t, we get e to the minus infinity. And that, of course, goes to 0. So this thing is going to, this function right here, e to the minus at, is going to produce this 0 here. The other part, e to the minus j omega t, well, this is remember, this is just an imaginary exponent exponential function which oscillates. If you use Euler's formula, for example, this thing has a cosine and a sine term, so it's just wiggling back and forth. But the key thing is this part out in front is going to go to 0 when we plug infinity in for t. So that forces this to be 0. And then we have to say, we have to subtract the value when t is 0. So if we plug in 0 here, we get e to the 0, which is, of course, 1. and here is again is e to the minus 0, and that also is 1. So we have 1 times 1, so we have minus a 1. Okay, so this 0 minus 1, that minus sign cancels this minus sign, and here is our answer after the dust settles here. Our Fourier transform for the signal is 1 over a plus j omega. So here is our result inside the red box here. Now the good news here is that we're not going to have to do this every time we see an exponential function like this, and we're going to see this very often for the remainder of the course. Instead, whenever we see an exponential function like this, we're just going to use this result here, depending on what the value of a is. We just fit that. We just substitute the value of a in down here. So we'll do some examples of this on the next slide. So what does this Fourier transform tell us? Well, obviously this is a complex function, right? It has real numbers, the 1 and the a, and it has an imaginary part. Here's the j omega. So in order to make sense of this, we will plot its magnitude, which is given here, 1 over square root of a squared plus omega squared. By the way, you did this back in homework number 1. So if you've forgotten about that, how to do that, look it up, go back and take a look at homework 1. And then here, likewise, is the phase. So we plot magnitude in phase. The phase is taken by inverse tangent of the imaginary part over the real part here. So if we look at the magnitude here, this function looks something like this. Okay, it has a peak at 0 radians per second, and as omega gets larger, it decays, right? Because when you can think of this, when omega gets big, it's down here in the denominator. Our Fourier transform gets smaller. So this is what the signal looks like in the time domain up here. This is what the signal looks like in the frequency domain. Okay, here are some examples or activities that you can do to practice your skills now with taking simple Fourier transforms. So we're going to use the Fourier transform pair that we just derived on the last slide. And again, this is an important result. We're going to use this again and again, so it's good to get kind of used to working with it. So we found on the last slide, we proved that if a signal x of t is equal to e to the minus at times a step function u of t, then its Fourier transform is given by 1 over a plus j omega. So in this set of examples, you're supposed to find the Fourier transform of this signal right here, and then also find the Fourier transform of this signal down here. So you can do this by simple inspection of these results here. So go ahead and pause the video, get out your pencil and scratch paper, and see if you can figure out what these two Fourier transforms are here. So here are the solutions to those two activities. Let's see if you got these right. Basically, all you're going to do here is look at this function here, and you can immediately see that if you compare that to this up here, a is equal to 2. So all we have to do is substitute 2 for a here. So we get 1 over 2 plus j omega. For the second one, you can see that a is equal to 3. Okay, so that's going to give us the 3 down here. And this 2 out in front is just a coefficient, and so that's just going to give us a factor of 2, which I'm going to put up here. The other thing I should mention here, hopefully you caught this, is this signal is not called x of t, it's called y of t. So our Fourier transform, we're going to want to use an uppercase y, not an x like this first one. So the Fourier transform pair can also be used to find the inverse Fourier transform. And so again, we're going to use this same Fourier transform pair, but now we're going to work backwards. We're going to start with something over here on the right side, and by inspection, we're going to write the signal or the function in time over here. Okay, so in this example, you're asked to find the signal, little x of t, that has the following Fourier transform. All right, and so again, you can do this. You don't have to do any integrals or anything like that. Just do it by pure inspection of this result here. And the second one here is a little more tricky and challenging. you have to find the signal y of t that has the following Fourier transform. Here, at first glance, you won't be able to do this because it's got this pesky 2 out here in front of the j omega. So you're going to need to figure out a way mathematically to get rid of that 2 in front of the j omega so that you can use this result up here. So again, go ahead and pause the video and see if you can figure these out on your own. All right, so here are the solutions to these inverse Fourier transform problems. So the first one was the Fourier transform x of j omega was equal to 7 over 4 plus j omega. So by comparing it to this form here, you can see that a is equal to 4. So this a over here is going to be a 4. So that's why we have e to the minus 4 u of t. And then the 7 up on the top, that's just a coefficient that goes out in front. So we can put the 7 in front of the e to the minus 4 times step function u of t. Now, the second one was a little trickier. Here was the given Fourier transform, 3 over 6 plus 2 j omega. We have to get rid of this 2 here in order to get it in the form shown up here. So the way to do that is simply divide every term by 2. And, of course, you're allowed to do that because if you divide the top by 2 and the bottom by 2, you basically not change the function at all. So the top becomes 3/2, or 3 over 2. And on the bottom, 6 divided by 2 gives us a 3. And then, of course, we're dividing by this 2 here to get rid of it. So now we've got this in a form that looks exactly like this up here. The 3/2, I can put that out in front, because that's just a coefficient or a multiplicative factor. And by inspection, I can see that the 3 here gives me the value of a, which I can substitute in up here. So I have 3/2 times e to the minus 3t times the step function u of t. Here's another activity for you guys to try at home, and this one is also important. It's going to show up many times in this course. The task is to try to find the Fourier transform of the impulse function, the delta function, delta of t. And so here is your hint. This is the integral for the Fourier transform. This is how you find the Fourier transform of any signal. So go ahead and substitute this delta function in for the signal and see if you can compute this integral. So again, please pause the video and give this a shot and see what you come up with. Okay, so how do you find the Fourier transform of a unit impulse? So our signal x of t is the delta function, delta of t. So we're going to start with our Fourier transform integral. All we do is plug in for x of t, we're going to put our delta function. Now, remember how the delta function, whenever it's inside an integral, that's always good news because the delta function forces the integrand to take on the value of 0 for t, because the delta function, remember, has no value other than when t is 0. So what we can do then is set t equal to 0 inside this integral. So we have e to the minus j omega times 0, which is, I brought that outside because it's not a function of t anymore. And of course, e to the 0 just gives us a 1. What we're left with then is an integral of the delta function. But remember, an integral just finds the area under the curve, and remember the definition of a delta function is it has an area precisely equal to 1. So this whole integral goes to 1. So our Fourier transform of a delta function is very trivial. It all simplifies down to the value of 1. So what does this mean? Well, in time, remember what the delta function is. It's a spike, right? It's an infinitely tall function that's infinitely narrow. And in this case, it shows up right at time 0. The transform of this is a constant value of 1 for all frequencies, okay? So the unit impulse, in other words, is composed of all frequencies equally. This is the spectrum, the frequency spectrum of an impulse, okay? So one way to, it's kind of an interesting example of this is if you think of a lightning bolt, it's in a sense an electromagnetic impulse or pulse because it occurs very briefly, all right? And you have a lot of energy and it shows up and then it's gone, usually a split second later. One of the things about lightning is that it has it causes radio frequency interference at all frequencies. So in other words, if you're listening to your car radio, particularly an AM station, and a lightning strike happens somewhere, within the city or something like that, you'll hear that static, that crackle on your radio. It doesn't matter what station your radio is tuned to, because the lightning bolt's spectrum covers all of the electromagnetic spectrum, or at least practically all of it. We can likewise find the Fourier transform of a shifted unit impulse. So at this time, our impulse, it doesn't occur at time 0, it occurs at time t0, and so the impulse is over here, it's delayed. So x of t is delta function of t minus t0. This is a delayed or shifted impulse. So again, if we plug this into our Fourier transform integral right here, what this does is it forces the value of time in this function to be equal to t0. So we have e to the minus j omega t0, which I can bring out in front because this is just e to the some number. This is not a function of time anymore. And then, of course, what's left here is this integral. And remember, the integral of any delta function is always equal to 1. Even if it's shifted over here, it still has the same area under the curve, which is equal to 1. So our resulting Fourier transform is e to the minus j omega t0, where t0 is the value of the delay in seconds. So once again, the magnitude of this function is 1. So the magnitude of the Fourier transform is exactly like the previous slide. It's a constant spectrum with a value of 1. Again, this delta function here has all the frequencies in it. The only difference now is it has a phase that is given by this function here by finding the phase of this complex exponential function here. So these properties of the delta function and the Fourier transform of delta functions leads to a rather practical and useful property of the mathematical function of this delta function. So what we're going to do here in the next couple of slides is a bit math intensive. It's not super conceptual or intuitive, but we're going to use these results as they are very important. So the idea here is that the Fourier transform representation of the unit impulse finds its use in a lot of areas of physics and engineering. So what we saw in the previous slides was that if our signal x of t is equal to a delta function, delta of t, then the Fourier transform, big X of j omega, is equal to 1. So let's go backwards here and remember the synthesis equation, right? This is the inverse Fourier transform equation. X of t is 1 over 2 pi times the integral of the Fourier transform times e to the j omega t integrated over all omega. So for the delta function, we're going to let x of t be the delta function, okay? So we're just replacing x with delta. And of course, the nice thing here is big X of j omega is just equal to 1. So this becomes a 1, and we're left with this result here. This is a Fourier transform representation of the delta function. The delta function can be expressed as 1 over 2 pi times the integral over all omega of e to the j omega t d omega. All right, and likewise, if we take a delayed delta function, a delta of t minus t naught, then remember from the last slide, the Fourier transform was given by e to the minus j omega t naught. And again, we take the synthesis equation here and replace x of t with delta of t minus t naught, as shown up here. So we get this on the left. And then on the right, for x of j omega, we use this result here, stick that in there. And notice both of these exponents have an omega in it, and they both have a j. So we can pull out that j omega, and we have in parentheses t minus t naught. So this is the Fourier transform representation of a delayed delta function. Now, we can take this one step further and sort of generalize these results. When we're doing these integrals over, all omega, omega is technically a dummy variable because it disappears after we perform the integration. In other words, we can rename omega with whatever we want, and it doesn't change the results at all. So I'm going to just rename omega to x and rename t to y. So this is sort of a general mathematical form of a delta function. A delta function in terms of y, whatever variable y can be written as 1 over 2 pi times the integral over all x of e to the j x y. Now these x's and y's can be any variable we want. They can be time, they can be x, they can be y, they can be omega. All we have to do is substitute, we're just basically renaming variables. And likewise, this is the version of the delayed delta function, delta of y minus y naught is equal to 1 over 2 pi times the integral over all x of e to the j, and in parentheses y minus y naught times x times dx. Okay, so this is, I know this is sort of abstract here because x and y here can represent anything, but we can use these forms to help evaluate expressions, and we're gonna use these. These will show up occasionally in this chapter. So here's a little sort of a math exercise for you to try. I'm giving you this just crazy looking integral down here. Your task is basically to use these results right here to evaluate this integral and also plot what the integral looks like, either in time or frequency, whatever the case may be. So go ahead and pause the video and see if you can do this using these results here. All right, so here is the solution to the activity. Again, these are the two integrals from the last slide that, these are the generic forms of the delta function that we're going to use here. And this was the integral that I gave you. So there's a couple things we can do here. First of all, e to the j pi. Remember that on the unit circle, this is just -1. All right, because pi is 180 degrees, so when we go over on the unit circle, e to the j, times 180 degrees, we end over at -1. So this e to the j pi we can bring out in front and just change it to a minus sign. What's left inside, I've sort of combined these two exponents here. I have e to the j times omega minus pi all times t times dt. All right, now what do I do with this? Well, what I do with this is I look at this form over here and I see that it looks just like this integral here if I make some substitutions. I'm going to let t be x and I'm going to let omega be y. All right, and so when I do that, and notice I can multiply both sides to get rid of the 1 over 2 pi, I can move the 2 pi over here, okay, and put it in front of the delta sign. So I end up with this integral here is equal to 2 pi times the delta function of omega minus pi. Okay, so if you're not sure how I did that, write it out on paper and make those substitutions. It's just basically comparing this integral here to this integral here and renaming the variables accordingly. So what I'm left with is a minus 2 pi times the delta function of omega minus pi. Now, what does this thing look like if we graph it? Well, this is a delta function not in time, but a delta function in the frequency domain. And this delta function appears when omega is equal to pi. Because remember, the delta function only exists when the argument is 0. So this occurs when omega is equal to pi. So this is what I guess you could call this a spectrum of this, whatever this represents here. It is a delta function sitting here at omega equal to pi, and furthermore, the weight of the delta function is -2 pi. So I've put that up here. You could also draw this pointing down if you wanted to, with a weight of 2 pi. Okay, so here's another activity that is actually somewhat related to the one that you just did. So this one is a little more practical. What does the Fourier transform look like of your car battery? All right, so let's assume you have a old-fashioned gasoline combustion engine car with a 12-volt car battery. All right, so what does the Fourier transform of your car battery's voltage look like? So how do you do this? Well, I've given you two hints. You're going to need to use both of these integrals. This is the integral for finding any Fourier transform, right? This is the definition of the Fourier transform, so you're going to have to use that. And the other integral that you're going to use in order to solve it is going to be this result. Again, this comes from the last couple of slides. This is the sort of generic form of a delta function. Okay, so you're going to have to swap some variables in order to do this. So see if you can figure this out. Please go ahead and pause the video again and give this a try. Okay, let's see if we can find the Fourier transform of a constant signal or a DC, direct current signal, such as that of your car battery. So let's let x of t, our signal, be some value a. All right, so this is a little more general. Obviously, in the one that you did, a is equal to 12. All right, that's the voltage of your car battery. And your car battery, of course, its voltage, we're going to assume stays at 12 volts over all time, okay, because it's constantly being recharged and so forth. So in time, the car battery just looks like a constant function at 12 volts. So we need to plug this value of a, whatever it is, 12, into this integral here. So when we put a in here, a is a constant, so I can bring it out to the front of the integral. Now that leaves me with an integral over all time of e to the minus j omega t times dt. So what do we do with this integral? Well, we use this result here to evaluate the integral. Notice that this integral here, if we let x equal t, and if we let y equal omega, then we get this integral. Remember this 1 over 2 pi? You can move the 2 pi in front of the delta sign, right? So in other words, 2 pi delta y is equal to this integral here. And so by making those variable names switches, we end up with our result 2 pi times a, and in your case a was 12, times a delta function of negative omega, all right, just by, again, comparing this to this. And the delta function of negative omega is the same as a delta function at omega. All right, it only occurs when omega is equal to 0. So what does this look like? Well, this is our Fourier transform of your battery. It's equal to 2 pi times, in your case, the a would be 12. So this would be 24 pi, and it is a spike in frequency that occurs at 0 radians per second. Now, what does this mean physically? Well, it makes sense, believe it or not, because think about what this function here is showing us. There's no variation, there's no change in this function. So what is the frequency of your car battery? Well, it's 0, right? It has no frequency. It has 0 frequency. So we expect the transform to show up only at 0. In the frequency domain. So this spectrum here tells us that this is a constant function with 0 frequency. And interestingly, there is a dual nature here that shows up all the time. Because remember when we found the Fourier transform of a delta function, which in time is a spike, then the transform was a constant function of frequency. So notice these are converses of each other. A constant signal in time gives us a spike in frequency, whereas a spike in time gives us a constant spectrum in frequency. And the reason for this dual nature is not a coincidence. It has to do with the fact that the Fourier transform pair, remember those two integrals, there's the inverse Fourier transform integral and the Fourier transform integral. Well, they are very similar to each other mathematically. They have a symmetry built in. One of them has a transform, the other has a signal in time, and so they end up sort of being, there's a duality to them, and we'll see this property again and again as we go forward in the course. Let's take a look at another example of a Fourier transform. This time, let's do it for a rectangular pulse. So this is, something that comes up fairly often in a course like Signals and Systems, where the signal is just this pulse, this that shows up for some duration. Here, the duration is given by 2 times uppercase T here. That's T. Big T here is what they call the half width of this pulse. And just to keep the math simple, we'll let the pulse have a height of 1. So if this was a voltage pulse, it would be 1 volt that shows up for, let's say, 2 seconds or something like that, okay? So what does a Fourier transform look like? Well, all we have to do is basically plug this pulse into the Fourier transform integral. So x of t here, you can see, has a value of exactly 1. So that's easy. This is going to just turn into a 1. But it only appears from minus t to positive t. And, here I'm talking about uppercase T, okay, which is the half width. So we replace this negative infinity with minus t, and we replace that with t up here. So this is again, a pretty standard trivial integral. This is just an integral of an exponential function. So by now, you certainly know how to do this. Anything in front of the t, you bring out in front 1 over that. So we have minus 1 over j omega times e to the minus j omega t, and we evaluate it from negative t to positive t. And so plugging in those values to do the integration, we end up with this form here. I'm going to take this minus sign and distribute it inside, which will just flip the order of these two, and I get this form here. I'm not going to read off all this stuff. You can read it faster than I can say it. And then to simplify this thing down and make some sense of it, we're going to do a little trick here. We can, let's see, we can multiply and divide by a factor of 2. So notice in this term out here, 1 over j omega, I inserted a 2 here, and I took it back out down there. Now, the reason I did this is everything, if I block off this first term, everything that you see to the right of my marker here is precisely equal to a sine function by the Euler identity. Okay, so all of this stuff here, from here on, just becomes sine of theta, and theta is equal to omega t. So we can simplify this thing down. The Fourier transform is 2 over omega times sine of omega t. Now we could just leave it like that, but we can actually simplify it a little bit more. Recall the Sinc function. Sinc of theta is defined as sine theta divided by theta. And remember, it has this kind of, it has an oscillating form where the oscillations die out over theta, or time. And so what I'm going to do here is, notice I've got sine omega t, and then on the bottom I've got an omega, but there's no t. Well, that's easy to fix. Again, we do a little trick. Put a t in out here and take it out down here. So this t and this t technically cancel each other, but that's how we can put them in there, of course. But I'm going to leave it in there because I want everything here inside the parentheses. I'm going to use my definition of a sinc function, and here's the final result, which is, fairly compact in form. The Fourier transform of a rectangular pulse is 2 times the half width. In other words, this is the width of the function, times the sinc function of omega t. So this is what our Fourier transform looks like. These are the frequency spectrum of a pulse looks like this. And we can sort of do the same thing, but working backwards. In other words, we can find the Fourier transform of a sinc function. So this time, let's work backwards because the math is a lot easier. Suppose we have some function whose transform or spectrum, x of j omega, looks like a rectangular pulse. But remember, this is not in time. This is in frequency. So this is what we call a band-limited signal, basically. The frequencies of this signal only go from negative W to positive W, where again, W here is the half width in frequency. So what we're going to do is not find the Fourier transform, because this is the Fourier transform. We're going to find the signal. So we're going to use the inverse Fourier transform integral, or the synthesis equation. And we're going to plug in for x of j omega, we're just going to plug in a 1. And these values of omega, negative w to w, tell us what to put in for the limits of integration over frequency. So you can see the minus w here and the positive w here. And again, this is just a standard, simple exponential function that we have to integrate. So, again, the 1 over j omega comes out in front, and we're going to evaluate this thing from w minus w to positive w. And so sticking those values in, we get this form here. Oh, by the way, I think I misspoke up here. Remember, we're integrating over frequency, not over time. So we bring out the j and the t and put that on the bottom. So it's 1 over jt, and then of course the 2 pi was already down there. So that's how we ended up with this. We're not integrating over time here. We're integrating over frequency. So you just have to be a little careful here and watch our variables of integration. Anyway, when we get it in this form, we kind of do the same tricks. We turn this thing into a Sinc function using the definition of Sinc function. So in order to do that, notice we have a t down here, but there's no w like there is in here. So we fix that by multiplying by w and dividing by w, and now all this stuff in parentheses becomes our Sinc function of w times time. So what we've got here is, for this transform shown up here, our signal is basically a Sinc function, okay? Here's one more example of computing a Fourier transform. And in this one, this is a Gaussian pulse. And this one has some important applications in more advanced courses, for example, on communication systems involving fiber optics and light pulses sent over fiber. A light pulse sent through a fiber optic cable is not really an ideal pulse with sharp edges and everything. It looks sort of like a Gaussian function like this. So it can be modeled, this could be the model of a pulse that occurs on a fiber at any given point. As that pulse goes by, it might trace out a shape like this. And so this is, you'll remember again from your math class, this is a typical form of a Gaussian function in time. It's an exponential function, e to the minus a, but the difference now is that there's a t squared up there, and that's one of the markers of Gaussian type functions. And the value of a will determine the width, the sigma or the standard deviation of this Gaussian pulse. So if we want to figure out the Fourier transform of this thing, of course we're going to use our Fourier transform integral here. We're going to substitute in our signal x of t for this Gaussian signal here, and you can see I put that in there. Let's see, the next thing here is I can combine my two exponents here by simply adding them together, and I end up with this form here. E, and look at the exponent, minus a t squared minus j omega t. So what do you do with this? Well, this is something that would not be super easy to integrate using standard methods, but we can pull this off of an integral table. This is one of many forms of what they call Gaussian integrals. So if you look up in a table of Gaussian integrals, you'll find one that looks something like this form here with a's and b's, and by comparing them, you can see we've got the same a, but the b obviously is going to be negative j omega. So this is the solution to this integral in terms of a and b. So by making the appropriate substitutions there, we get the following form of our Fourier transform. And so what happens here is this minus j is squared, and remember j squared is just negative 1. So that can't and then this minus sign here is squared, which becomes positive. And so we end up with a Fourier transform that is also a Gaussian function. Notice it's e to the minus omega squared over 4a. And so this is a Gaussian form in frequency, just like this is a Gaussian form in time. So the Fourier transform of a Gaussian pulse is a Gaussian spectrum in frequency. And this is one of the interesting things about the Gaussian function, is that its transform has the same mathematical shape as the signal. And to my knowledge, this is the only type of function that has this type of characteristic, where both the time domain and the frequency domain version of the signal are both mathematically similar in that they're both Gaussian functions. Okay, so finally, here's our last slide of this part of the video. I just wanted to again point out this idea of the dual nature of the Fourier transform pairs. We've seen this now in several examples where there is a duality seen when we switch between time and frequency domains. So in other words, when we had a square pulse, we got a sinc function for a square pulse in time gave us a sinc function in frequency, whereas a sinc function in time gave us a square spectrum in frequency. So you can see the duality here when we switch frequency and time. And of course, we also saw this with the delta function. We talked about this one earlier. And again, this is not a coincidence. This is due to the symmetric forms of the synthesis equation for little x and the analysis equation for the Fourier transform uppercase X. Okay, that is it for this part of the video. I will see you shortly in part 2 coming up next. Goodbye.